Assalamu alaikum, sir. Today I will present on right optimized index structure in database management system. Meet our teammate. This is me, Jannati, Humayra, Akter, Himu. Rest are as follows: Mahir Faisal, Sahela Ahmed, and Faisal Hossain Khan. Index are special data structure that improve data retrieval speed. Just like a book, index help us jump to the right page. Database index help us find records quickly. But there is a trade-off. While index makes reading faster, they often slow down reading operations such as insert, update, and delete. That's why right optimized index are so important. Motivations. Traditional B plus trees are excellent for a read heavy workload. However, they struggle with random writers because each insert or delete requires random disk access. On HHDS, seek time limits performance to about 100 writers per second. Even SSDs face expensive erasers operations. So the goal is to design structure that converts random writers into efficient sequence writes. HSDS suffers from random HSDS suffer from randoms IOs because of physical head movement. SSDS are faster, but random writers are costly because page must be erased before writing. So basic B plus trees are not suitable for high frequency random write workloads. Thank you. Now I would like invite my next teammate.
Assalamu alaikum, sir. I'm Sahela Ahmed, ID 2411596. Now I will introduce LSM trees. LSM trees stands for log structured merge tree and it is specially designed for write heavy workloads. Traditional index structures like B plus trees perform many random disk writes which are slow. To solve this problem, LSM trees first store incoming data in memory and later write it to disk it is sequential way. This reduces random disk I/O and improves performance. The structure uses multiple levels. Level 0 stays in memory and as a small B plus tree, which level 1 and level 2 higher levels are stored on disk as larger B plus trees. An important idea here is that data does not go to disk immediately. Instead, it moves from memory to disk in batches, which makes the writing process much more efficient. Next slide, please. Here we can see the overall structure of an LSM tree. At the top, we have level 0, which is in memory. All new insert and write operations happen here first. This makes the system very fast because memory operations are quick. A large portion of memory is allocated to this level so that it can handle many incoming writes. When level 0 becomes full, the data is moved to the next level, which is level 1 on disk. This process is called flushing. As we go down on level 2 and level 3, the size of data increases. Each level is larger than the previous one. So, overall, the architecture follows a hierarchy where data flows from memory to disk gradually. Next slide, please. Now let's look at how insertion and merging work in LSM trees. First, all new records are inserted into the memory level, which is level 0. This ensures that writes happen at memory speed, making the process very fast. When level 0 becomes full, its data is moved to disk at level 1. Now, when a disk level becomes full, a merging or compaction process starts. In this process, data from one level is merged with the next level. During merging, data is scanned in sorted order and combined. Similar to the merge step in merge sort, a new tree is then created from this merged data using a bottom-up approach. The most important benefit is that many small random writes are converted into one large sequential write, which greatly improves disk efficiency. That's all from my part. Now I would like to invite Mahir to continue the presentation.
Thanks, Sahela. So, in this part, I will talk about the main benefits of LSM trees and how they handle delete and update. And I will explain the buffer trees later. First, the benefit of LSM trees. The biggest advantage of LSM trees is that it writes data sequentially. That means instead of writing data randomly all over the disk, it writes in order. Because of that, the system becomes faster, especially when there are a lot of writes. Another good thing about that is it averts random disk access, so the system doesn't have to keep jumping from one place to another place, which saves time. Also, LSM trees keep the data in full blocks, so there is less waste time and fewer operations. Now about the delete and no, please, the previous slide. Now about delete and updates. In normal system, when you delete something, it gets removed immediately. But in LSM trees, it doesn't work like that. Instead of when we delete data, a small marker called tombstone is added. So the data is marked as delete. The actual cleanup happens later during something called compactation when data is merged. The approach helps to avoid slow disk operations. Next slide, please. Now now we will like to discuss advanced LSM operation. In this process we will be discussing about step merge index, which uses multiple trees per level to reduce the merge cost, like Bloom filters used to speed up lookups, check if a search key exists in a specific tree without reading the disk. And for real world LSM implementation, big database like Google, Bigtable, Apache HB base, and NoSQL database like Apache and MongoDB, LevelDB used, where data grows rapidly and uses high speed ingestion. Next slide, please. Now let's move. This is introduction to buffer trees. Buffer trees are another way to improve write performance. The idea is pretty simple. Instead of sending data directly to disk, data is first stored in a buffer. Each node is the tree. Each node in the tree has its own buffer. Next slide, please. How buffer tree works: at first all the data goes to the root buffer. When that buffer becomes full, it doesn't send one by one, it sends many records together for the next level. This is called batching. Because of this, disk operations become fewer and more efficient, so overall performance improves. Now next slide. Now I would like to call my next teammate Faisal Khan.
Assalamualaikum sir, my name is Hossain Khan, ID 2411503. So I'll be talking about the challenges of this presentation. So first of all, read amplifications. So queries may need to scan multiple levels before finding the data, and write also about writing info amplifications, for which data gets rewritten several times during merges. High resource usage, for the background merging consumes CPU memory and disk bandwidth, and also latency spikes, which means compaction can temporarily slow down user queries. And for yeah, and then we have the storage overhead. Tombstones and multiple versions of data increase space uses. And for the last, the complexity, more difficult to tune and maintain compared to traditional indexes. So we also found some solutions. The solutions have like Bloom filters. reduce unnecessary disk reads by quickly checking key existence, sequential writes, convert random writes into efficient sequential disk operations, batching updates, group multiple records in memory or buffers before flashing to disk, and also leveled merging, balance write throughput with query performance. And for the fifth one, compaction strategies, smart scheduling to minimize query disruptions, and for the last, hybrid approaches such as combining LSM with learned indexes or coaching layers for efficiency. So let's talk about some applications of this presentation. So these are used in such as distributed database, Google Bigtable, Apache, Cassandra, HBase, storage engines like RocksDB, LevelDB, big data analytics like real-time ingestion of logs, metrics, also social media platforms like handling millions of posts, likes, and comments per second, IoT system, continuous ingestion from millions of connected devices, and also financial systems like high frequency trading and transaction logging. So for the conclusions, the LSM, we can say that the LSM trees are best for massive intensive heavy workloads, highly efficient for sequential disk access. And the buffer trees are alternative approach for batching writes in buffer B plus trees, good performance on SSDs. So workload trade-off, and also for the workload trade-off, the choice between these structures depends on the specific applications which need to balance high-speed data ingestion with efficient search capabilities. That's all for today. Thank you for your attention.